Okay, so good morning, good afternoon, good evening, whichever applies to you. And thanks for coming to the mini symposium. My name is Cecilia Gonzalez Stockman from the University of Queensland, and it's my great pleasure to introduce our next speaker, Francisco Beron-Vera, who is a professor at the Department of Atmospheric Sciences at the University of Miami, and he will be talking to us about reactive ocean currents.
Thank you, Cecilia. Thank you, Gary. And I think I should thanks also Peter, although he's not there, for giving me the opportunity to talk about these things. I changed, as you have seen, a little bit the title of the talk. I'm not gonna disappoint you if you were expecting me to talk about ocean, because I will. I will be talking about some of the stuff that I originally described in the abstract. So this is work in collaboration with a number of people, Josefina Olascuaga, Philippe Miron and Rasmus. This is a result of work that, application of ideas that we learned from Peter Koltai and his student, Lucy Hetman from the University of Berlin. We have also people collaborating with us in some of the applications that I'm going to discuss. Susan Lozier and her student Kimberly. And then we have other people that I need to mention, Nathan Putman, Joaquin Trinanes, Rick Lampkin, and Gustavo Goni, that are collaborators in another part of this work that I'm going to be describing. So this is going to be a talk on discrete transfer operators, transition matrices, and in particular about the transition path theory. I'm going to go over that first. I'm going to review the basic elements of that. I'm going to talk about a little bit of time asymptotic almost invariant sets, and time permitting, I'm going to try to cover examples with actual data in the ocean. The Malvinas current, the Great Atlantic Sargassum Belt. It's something that has been of interest to us lately. Garbage patches, Gary, I guess he's familiar with that for work that he's done on that, and deep ocean circulation things. So this is the basic setup, transition path theory. This follows work introduced by, or the ideas introduced by Wijnen and Eric van den Eyden in the papers that I'm pointing out here. So what we have is a Markov chain, discrete time, homogeneous, and what we have is okay. What do I mean by that? We have a transition matrix controlling the probability of transitioning between states I and J in a chain, and we're going to be assuming that the chain is in stationarity. That means that the random position of T distributes like the stationary distribution of P. In order for that distribution to exist, I need to make some assumptions on P, and those are of irreducibility, meaning that starting on any state of a chain, the chain is visited, and aperiodicity, meaning that no state is visited cyclically. P has the property of being invariant, and applications on of this discrete transfer operator P, and is reachable from any distribution and the limit of infinitely many applications of P. Things to have in mind, this matrix, we call transition matrix, is row stochastic, meaning that the sum of each row of a matrix equal to 1. What does TPT? TPT looks for certain types of trajectories that have this property. Given two sets in this phase space A and B, we're interested in trajectories that connect A and B directly. So I'm showing here a long trajectory and the pieces that are identified as reactive trajectories. This transition path theory was introduced in the context of, in the study of chemical reactions. For that reason, A is traditionally being identified with the reactant and B with the product. We don't have that in the ocean, but we see a number of applications in which these ideas, I mean, what I point is that these things have been developed to study rare events. I mean, transformations in chemical reactions. This is not what we have in the ocean, but we do have, we believe, I mean, depending on how we treat the data, Markov chains, so we can look at this type of trajectory and make sense out of them. All right, just a little bit of what we need to be able to identify those spatial trajectories are two main objects, and those are the forward and the backward committers. In here, what we have is tau plus and minus. This is a random variable that gives the first entrance and last exit times to a set in phase space, and the forward committer says that if a trajectory starts in state I, will hit the target set B and not A in forward time. And the backward committer would say that starting in I, we come first from A and not from B. So this is a way to make this idea formally. The point in here is that the committers, which we need to compute other things, are computable directly from the transition matrix through these expressions in here. In particular, if you're thinking about the forward committer and see that A is the source and B is the target, so the forward committer is going to be 1 there, it's going to be 0 there. It's going to be other way around for the backward committer. With the forward, the backward committer, you can compute what we want. So this currents of reactive trajectories, which gives is the probability of you can say like this, is the average number or average flux of trajectories going from state I at time n to state j at the next time in its way from A to B directly. In practice, one is interested in the effective current, not just the current, and that you need to compare the amount of flux going from A to J with that from J to I. So these are going to give us the most likely transition channels, and these are the ones that we want to frame. Okay, and why cannot? Okay. All right. A little bit of technology advance, mainly due by Lutzi. We are working on a paper, hopefully going to be submitted soon, is that the original formulation of the TPT works for closed systems, but for the many applications that we're interested in, we are dealing with open systems. So basically, we don't have a stochastic matrix, but actually sub-stochastic matrix. And we want to make it stochastic some way. So we augment, in a way, the transition matrix by including a state omega that is traditionally called nirvana, but we call it two-way nirvana because we send any imbalances to nirvana and we send them back to the chain different ways. One way of doing it is go and take the quasi-stationary distribution of the transition matrix corresponding to this open system. We're going to be trying different things. It turns out that the formulas from TPT remain the same, with the only difference is that whenever we have P, what you have to do is just replace P by PO, which is the substochastic P, and instead of using the stationary distribution, we replace it by the stationary distribution of the augmented P restricted to O. This is different than this in general. I did not mention that P minus in here is the transition matrix for the reverse chain. So those are all the elements that we need in order to identify these trajectories. I'm going to talk about also a little bit in the applications of almost invariant sets. This is stuff that Delnitz, Oliver Young put forward together with Gary and Peter contributed to that. And the stationary distribution is the left eigenvector of the transition matrix corresponding to lambda equals to 1, which is the only one, provided that P is ergodic and mixing. And as it's invariant and it's limiting. In a sense, we can think of this as an invariant attracting, highlighting invariant attracting distributions. The right eigenvector, because of rho stochasticity, is constant. So you can think about the whole space as a basis of attraction for P. But the eigenvectors left and right of P have a property of highlighting certain parts which are not going to be invariant, but going to be almost invariant. The closer you get to lambda, the slower these sign densities are going to decay. The right eigenvectors tend to show plateaus. There are also sign densities, and they are expected to form basins of attraction for the almost invariant sets identified by the left eigenvectors. I'm showing this here quickly. You may be familiar with this, with diffusing motion in a triple wheel potential, satisfying this stochastic differential equation. The stationary distribution P, I mean, this is something that can compute actually analytically, but what I'm doing here is discretizing using Ulan's method. I'm not gonna show the, I'm going to talk about more of this in the next slide when I'm dealing with actual data. See that the three wells are identified. I mean, the stationary distribution maximizes in these three wells. And this first subdominant left eigenvector identifies these two wells. The third subdominal, start to show the third well. What I'm plotting here are the basins of attraction of each of these three almost invariant sets by putting together the corresponding right eigenvectors using SIBA introduced by Gary, which seeks a rotation of a collection of eigenvectors that brings them close to a binary collection. I mean, it's something like, because we are trying to identify these plateaus, we can use clustering algorithms to do that. So this is all that I need to go into the data. This is what we're typically going to have. I'm just showing an example in the ocean with the actual trajectories. It doesn't matter what they are right now, but this is going to apply generically for the stuff that I'm going to be describing next. So we have trajectories on a certain domain. We put a grid in there. So we cover the domain with boxes BI, and we have observed trajectories, and we can approximate the transition matrix by simply counting the number of trajectories that are in BI at time t, and they are and Vj at another time, actually t plus capital T. And we do this for any t because we don't have enough data to go non-autonomous in here. And we need to see what we do with capital T, which is the transition time. The way we typically obtain a value for T is by looking at the autocorrelation of these trajectories. For surface buoys in the ocean, this is typically of the order of 1 day. So you're going to be using either 2 or 3 days, something longer than the autocorrelation time in order for the Markov assumption to hold. We've been a little bit more careful in the applications I'm going to show than we have done in the past, in a sense that we try to check whether the Markovianity assumption holds. And this is by comparing what happens with P computed over a long transition time versus taking P over a shorter period of time and multiplying that. And this is what we are showing here, basically the eigenvalues of this. And they fall kind of close to a straight line. So the Markovianity assumption works well in most situations. First is an example in the Southern Ocean where okay, we have the Malvinas current in here. We got interested in this situation because of certain features that we observe in the ocean, these boomerang structures in here that suggested the presence of a certain structure. We call it shear plus parabolic structure in there. And the idea of this is that this thing doesn't prevent the mixing from stuff on one side and on the other side. And this is what we are testing here with actual trajectories. This is computed from altimetry. Certain, there are altimeters that measure the sea surface height. We can get velocity from there. We can go and apply certain techniques and extract these. But we can also go and use trajectories from drifters. These are the type of drifters we're going to be using. There's a ball floating at the surface, and attached to it there is a drop that make the buoys to follow as closely the motion of the water. And we've been able to compute this geography of basins of attraction that shows a partition of the domain. So the red is not mixing with the blue or the yellow. So it was a good place to test these ideas to see if we can, what we can do when we apply TPT, transition path theory in here. First thing we did, we just ignore the trajectories that went out of the domain. So we have a closed system, and we applied TPT, and we've been able to identify the Malvinas current as a reactive current. If you go, I mean, by not constraining the place of the target, the flow goes in here and has to go up somewhere through here. But if you constrain the target to be in an unphysical place, you see these fuzzy trajectories in there. We can also go and apply a different closure, and this is taking into account that actually there's water flowing out, and so we add an Urbana state in there, and we send all the imbalances back into the chain by making all the stuff that is out a single box and looking for the transitions in that way. This way, we're able to isolate the current more cleanly, and compare to the situation in which we put the target in this unphysical place. You compare the probability is much lower than the probability in this case. This is for the Malvinas current. Next application that I have in mind is something that I've been working with collaborators recently, and it's this thing that I'm showing here. So what we have, this is motivated by observations from satellite observations of sargassum, that show that in addition to sargassum being concentrations being important in the Sargassum Sea, in the Atlantic, or in the Gulf of Mexico, there's a large, lots of amounts of sargassum in what is called the Great Atlantic Sargassum Belt. And the people in the Caribbean Sea are very aware of that because of the economical problems that the inundations of sargassum are producing. What I'm showing here are evolutions. We computed a Markov chain with the data, and we push forward just a uniform density, but using the same data that I used before, and trajectories of the same buoys, but when they lost the draw. And these are more affected by wind, and see that the distribution looks more like this belt than when you take into account the motion of the water. So this is pointing to the direction that sargassum is more affected by wind than actually they are the actual currents in the ocean, TPT. So what I'm showing up here are the dominant, the first two dominant eigenvectors, left and right. And what you can see is that the if you want, the sargassum sea is decoupled from the region where the Great Atlantic Belt is located. Important questions are how the sargassum sea is connected with other regions, or how the northern west Gulf of Mexico connected with sargassum sea, or regions where sargassum is concentrated, and like is known to be concentrated, like in Brazil or in Africa. So we went and put a possible source of sargassum west of Africa and a target in the Gulf of Mexico. And we have been able to isolate our two currents, one that goes directly, like the sargassum, sorry about that, like the Great Atlantic Sargassum Belt is suggesting, and a southern current that spends some time circulating in the Gulf of Guinea, crosses the Atlantic, goes by the Amazon River mouth into the Caribbean Sea. This can have consequence for blooming, and when we're investigating that. I don't know how much time I have left. 2 minutes, perhaps?
Around 2 or 3 minutes, yes.
All right. So this is, of course, just an analyzing the motion of these buoys, but we have to be more careful because the sargassum is not just buoys. These are plants that live, they eat, and these are not isolated particles. So we have developed a model to deal with that. So this is, I was tracking this, but actually we should be tracking something more like this. It's a collection of particles connected by elastic bands, mimicking the flexible stems that connect the bladders that keep afloat the sargassum maps. So we develop a theory for the motion of these plants that is going to appear in the Journal of Fluid Mechanics soon, and the expectation is to be able to couple to this model a growth model. I mean, controlling the number of beds of particles in the rasps of sargassum as they are moving around in the ocean, encountering different temperature and nutrient conditions that will make them to grow or to shrink by dying, basically. All right, my talk actually was planned to be much longer than the time that I had available. So I'm going to skip this. I'm going to go directly to the last application here. Is deep flows, if I have time. So we go to the South Polar Gyre. This is north of the Gulf Stream. We don't have surface floats anymore, but we have these cylinders that are deployed and go below the surface, that are tracked by acoustically. Okay, the theory of abyssal circulation of stomel predicts that when the water sinks in these regions after releasing heat to the atmosphere, they should take a boundary current. There were a number of experiments in there lately. The importance of looking at these things is because when they sink, these deep currents absorb CO2. So it's important for climate. But if you look just at the trajectories of these floats, you don't see a clear pattern. And the idea that Stomel's theory was not right I mean, it's been questioned recently. So we went with Susan Lozier and collaborators, and we applied TPT in there a little bit, and we observed first that using this data, that the subpolar gyre shows two disconnected regions. The left in here has the Labrador Sea and the Irminger Sea, and on the right you have the Iceland basin. So Philippe Miron is attending the meeting. He went and put sources in different regions, possible sources of the water formation, and depending on where you put the sources, you can reveal a well-defined boundary current. In order for the well-defined boundary current to happen, you have to be on one side of this province of this minimal dynamical geography that with provinces that are weakly connected. I don't know, it was clear on this, but I think I'm gonna have to leave it in there, and I'd be happy to try to clarify what it wasn't actually very clear. Thank you for your time.
Thank you, Francisco, for